Okay, before the break, we were looking at linked list, which we've already seen the one built into Java quite a bit. Some really good programmers built that one, it works good. But there's occasionally a need to build our own data structures. And linked list is a good example of that. I started doing it in recursion because our textbook uses recursion. So when you look at that, you're gonna see that. Lots and lots of tutorials you'll see it done in recursion. And I said something during the break, I'll say it again for the video. If anybody's watching this later on the video. I did it the recursive way on my way through school in computer science classes. I've done that every time I've taught the Java class so far and still messed it up. That's much, much, much harder. Loops were invented because recursion is hard. So looking at the reference material in our textbook and a lot of tutorials, when you see it done, data structure done with recursion, take a moment and rewrite that, restructure it as a loop, and it'll be a lot easier to deal with, a lot easier to make sense. You'll just see it with recursion everywhere because that's a standard way to practice recursion in computer science classes all across academia. I wanted to talk about some other data structures. Some big ones are going to be trees. So we've seen trees, that's a hierarchical structure. A directory structure, just a basic tree. We have some root. At the very top, we have the root, and everything branches off of that. So all the stuff in the middle are called branches. And when we get to the end, like that, and that, and that, those are called leaves. Just normal terminology for a tree. It's a good way to structure things. A nice organized system, right? When we build our UML class diagrams, they kind of follow that, which usually in an object-oriented lecture, I make it a point to draw the picture, the tree of life from biology class. Kind of looks like that as well. It's the way humans naturally categorize things. It's a good structure, but it's also not bad for a machine. Our directory structures are in game engines that would have a hierarchical structure kind of set up like a lot of our game engines most popular ones will have that tree structure where there's a root, this is the level, and then all the other nodes attached to it. The folder, files and folders on our computer system go that way. It's a good structure. But what really shines as far as us as programmers, the one that will concern us, is there are other restrictions we can put on this tree. Like you'll notice I intentionally started up here at the root, there's 3 branches. That immediately messes up some the optimization, having a bunch of branches. So what we're really interested in would be a binary tree. There's several different kinds. I'm going to start with a binary search tree. And the reason I'm going to jump ahead and start with this one is this is one of our most important because for very, very, very large data sets, it gives us a very rapid way to search through a data set. We haven't talked about big O notation. So it has a big O of log n. That's a measure of how efficiency decreases as input size increases. So as we go to more inputs, how does that change the amount of time it takes our program to run? So obviously, if we have 3 inputs for a test case and then 3 million inputs in the actual application of that software we were testing, it's going to take longer to run because 3 million things is going to take longer to process than 3 things. But how much longer? Does it, if we go from 3 to 300, does it take exactly 100 times longer? Or does that larger input size also add some extra overhead there as well? So if we go from three inputs to 300 inputs, does it take 200 times as long? So there's that extra little increase there. That would be, so if it goes exactly right in line, 100 times longer, to go from 3 to 300, that would be linear. There's no change whatsoever. That's what we can always hope for. That's really a constant. So that's a big O of 1. Every time we increase an input, we get that much back. That's an ideal that is pretty much never achieved. A heap's about the only place that achieves that. We'll talk about a heap Thursday. I think it's on Thursdays. Or down. I'm pretty sure a heap is on Thursday. That's about the only time we'll achieve that. Usually there's some extra overhead involved, right? Because as we have more inputs, we're going to use more RAM to hold those, which means we don't have as much RAM for processing, which means that we have fewer resources to process with, so that it's going to take longer. And there's different ones. Logarithm of n is a good increase. It's going to relate to like graphing in your math class. We have lines, y equals mx plus b. So the main thing we're graphing there would be the slope of a line, just that steady increase. That's what we usually have. That would be a big O of n. But we can slope that off. Or it could get worse. It could get much worse. Traveling salesman problem is a classic problem. If there's a certain number of stops that the salesman has to make, you think of it like it's an old problem, but you could probably state it today in terms of UPS. UPS driver has to go out, make a certain number of stops, and get back to the starting point. What is the best route for them to take? And make every stop. What's the best order for them to go? The only way to check that is what's known as the depth first search. The term is based off binary search tree. We'll see that in why in a moment. But depth first means we have to check every possible route. The only way to calculate that is to time every possible route and then see which time was quickest. That gives us a big O of n factorial, which is the worst we could possibly get. Right. Factorials grow really quick, really quick. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1, so we're up to 6. Get 4 factorial is 24, 5 factorial is 120. 6 factorial is 6 times 120. 7 factorial, we're up in 5,000 already. 8 factorial is 8 times 5,040. So it gets huge really, really quick. Those are the worst we could get. Logarithm, you might remember if you saw it in math classes, logarithm curve kind of looks like that. So at first it kind of grows quickly, but then it smooths off. So it's getting bigger, but not fast. And the rate at which it gets bigger slows down. So binary search trees give us a pretty good efficiency as the thing we're looking at gets larger. Really, I just wanted to mention big O notation. We're not going to calculate it or anything. You will see it, but it's a measure of how efficiency is worse as input gets larger. How are we losing efficiency? So a binary search tree is we restrict it so that there are only binary branches only binary branches from any node. So we only have two branches from any given node. At most two. To most. Obviously, 0 is going to be okay because eventually we're going to get to the end of the tree. And if we only have one branch, that's fine. What we don't want is 3 branches or 4 branches or 7 branches like we would have in our documents directory structure on our computer. A whole bunch of branches on that tree. So we're restricted to 2 branches at most. And then we sort the things. Sort by placing smaller elements to the left and larger to the right. So that's basically what our nodes are always going to look like. We have at most 2 branches, so we go ahead and name them left and right. Which, let me write this: public class pre-node. That sounds like a good name for it. So again, the Java code is a lot like what we saw earlier. We have a node. We'll have some sort of generic type we'll fill in later. We'll figure out what that is later. And then as far as elements, we have the node itself. So something of type T, we'll just call that the element we're looking at. And then we have a tree node that we'll call left, and a tree node that we'll call right. And then we'll kind of iterate it through our list. So kind of like we just saw in the list. That's another reason I wanted to do that. We have that pointer going to the next thing. But here we have 2 pointers. One's called left and one's called right. And ultimately it makes the structure that is optimized for a computer to go through. It gives us really, really good efficiency. So we have our root. And then from the root, we have our left and right. And I'm going to abbreviate it because I'm on the board. Typing's easy, but writing with a pencil is a lot harder. So whatever our root is, the node to the left is smaller, and the node to the right is bigger. Same thing here. We'll have a left and a right, and maybe over here we just have a right. I'm getting ready to draw an example on that. But we end up with this tree where at most there's only 2 branches. And we can iterate through it, and with only 2 branches, I guess I forgot it when I wrote up the code, we need the comparable interface. Whatever our generic type is, T implements comparable. Ever not? That make it on the TV? I think it's the video still getting that. But we don't just need any generic, it has to be something with the comparable interface. We saw that before, right? Says we have to implement a compare to method that returns an integer. And then we define what that integer we get back is. Usually the easiest thing to do is just subtract, return the difference. Then positive is bigger, 0 is equal, and negative is smaller. But as long as we can put them in that order, then our left and right gives us a nice organized structure on this. So let's look at an example. I'll draw it here on the board. Is that blue marker coming through? Well, let's try to make that bigger. There we go. Yeah, I guess that's visible on the video. I couldn't tell how visible it was. So this was just a quick example of a binary tree. Let's do an actual example. So our data is just a bunch of data points. We could think of that like a list. Let's say 19, 7, 3, 52, 14, 8. So that's our data points. And we need to put it in a list. So we'll just pick the first one to be the root. So 19 is going to be our root. And then we'll go through our list and just add whether that's left or right. I ran out of room here writing code, but obviously there's going to be a condition when we add to the list. It's not just the next like we did on the linked list. We check the comparable to see if we need to add it to the left pointer or the right pointer. Smaller things go to the left, bigger things go to the right. So we're at 19. Next thing's a 7. 7 smaller, so over on the left, we'll put in a 7. Then we have a 3. Go back to the root. Again, we're going to just like we started at head every time for linked list, we'll start at root every time for a tree. 19. 3 is smaller, so 7. 3 is smaller, so we come all the way over. We can't go any further left, so we got our 3 in there. 52. We go back to our root. 52 is going to be bigger, so we go to the right. We can't go any further right, so that's where our 52 goes in. Next up's a 14. We go back to the root. 14 is smaller than 19, so we go left. 14 is bigger than 7, so we'll go to the right. And then finally we have an 8. So we'll go to our root. 8 is smaller, so we go left. We have a 7. 8's bigger, so we need to go to the right. 14, 8 smaller, so we need to go to the left. Oops, that's an R. R. It's smaller, so we need to go to the left, and then we get down, put our 8 in there. So we end up with a structure that looks like that out of those data points. Or that's a good way to represent it. And then this is our optimal way to have a computer search through data. Or not the optimal way. Balance, that's the word I'm looking for. Optimal balance, because this isn't incredibly impossible for the programmer to put together and to get really good results. There are better things that we can do, but they are really, 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 really hard for the programmer. This one is still easy for the programmer, and we get really good results. That's why it's one of our optimal things. Good results, easy to program, makes a nice balance, even though we could, in theory, do better. And now it comes to a matter of how do we walk through the tree? How do we search through our data? Because it's right in the name, binary search tree. I'll leave the label there. So really there are a couple of ways we can do it. Oh, nice. I have 3 colors left. I'll use the 3 colors. I'll start with red, and the basic way would be in order, an in order traversal. And in order, we put smaller things to the left, bigger things to the right. So in order is left, node, right. Then we have prefix. And for prefix, we do the node first. Pre refers. So we're referring to our node, right? It's in order. It goes between left and right. Tree, we do node, left, right. Or postfix, goes left, right, node. So it's the order we go through them in. Your calculator, ones with the buttons. The reason you may have tried to put together a GUI calculator at some point earlier and then realized that there was all kinds of trouble you were hitting. A calculator needs to use postfix. So we put our operations in here like this. Right? 3 plus 5 equals, and then stick that into a binary binary search tree, and go through a postfix. That's what you have to do with the calculator to make the buttons work right. If anybody tried that, come to see that show up in like an SDEV 120 class. If you do graphics, so there's only a couple of us around the state that show graphics in the SDEV 120 class. So if you had me for that class, or one of the other people that shows graphics for it, you might try to think, oh, calculator is easy, and then hit all kinds of problems. Same thing in SDEV 140. People are like, oh, calculator is easy. When they get to the GUI, they're at the end, final project, and hit all kinds of problems. Because in order to do that, you have to take your button presses, like elements in the list, and then feed that into a tree. So 3, plus, and operations are smaller than elements. So 5 equals. And then we go through it in postfix notation. Which actually this would normally be a balance tree. So we make the operation the root and then build things off that. 3, 5, and equals is smaller. So we go through that in postfix notation. If anybody tried to do a calculator and went to step 140 and were just wondering why it was so difficult, it's because we kind of have to do it this special. We have to put it in a binary search tree and progress through that tree in a specific order to make it work. The way humans press buttons compared to how a computer does things. You may have encountered that before, right? A computer, we can't say 3 plus 2 because plus addition is a binary operation. So the computer needs to know we're working with a binary operation before we give it 2 numbers. So we have to say plus 3, 2. Anybody's encountered that? If you type in list, that's how we actually type the stuff in list. If you get to assembly language, you'll see a lot of that. But for a human, we see our first number, then the operation, and that's how we punch in a calculator. But for a computer, you have to have that operation first. That's why operations are less than, that way they go all the way to the left, and we do the left stuff first. That's why that's a necessity. Operations are smaller than numbers. But a computer has to know that it's doing a binary operation versus a unitary operation, so that it knows the next 2 things are the numbers to perform that operation on. We can't do a number first and then an operation. It would just confuse the machine. But that's a little sidestep, just in case anybody hit that problem. That's a common thing to see. So in order, we start by going left as far as we can. When we can't go left any further, we'll grab that, and then we'll come back and grab any nodes and move to the right. So we start at the root, go left as far as we can. Can't go any further. So left, our first element is going to be a 3 here. Then we need to grab the node. So we'll come back around, let's come up, grab this node in the middle. We get 7. Then we go to the right, but we're still doing in order, which means we have to always go left first. So when we go to the right a little bit, there's something there, but we have something to the left first. So we always have to go all the way to the left first. So our right side actually comes back around and we get left node out of that. Does that make sense? So go left as far as you can, then start coming back, grab a node. And as you go to the right, you have to repeat that process. If there's a spot where you can go to the left, you have to do so again. Every time you go to the left, you have to go left as far as you can and then come back. So 814. Do you see a pattern forming yet? For in order? Well, we can't go any further right. So we come back around. We already went to the left. So now we're back to a node. Grab our node 19, and now we go to the right as far as we can, and we're done. So that sorted our list. That got us in sequential order. What's next? Prefix. So prefix, we grab our node first, then we go to the left as far as we can, and then we go to the right. And it's sort of a repeating process. So starting at the root, that's a node. So we need to grab that. 19, and then we go left. We can go further left. So we need to go to the left. Node left, right. Yeah. I didn't want to grab that on the way. Yeah, I think this way. Then we grab our 3 as far left as we can go. And now we need to node, so we went left, so now we have to try to go right, but our process starts over. We hit a node again. Yeah, we need to grab that 7 on the way. We hit a node on the way. So node, start moving to the left. Oh, we hit a node, grab that. I had to actually write it down. I thought I threw it through my head and didn't quite work right in my head. It was actually when I wrote the number down, I was like, oh wait, no, 7 goes next. We hit a node, then we get all the way to the left. Can't go any further left, so we grab our left element, which is our 3, and we start going back to the right. We come around, up, we already got a 7, so we'll keep going to the right, and we get hit a spot where we can branch off. It's not an endpoint. We have to decide whether we can grab it or not. Which means we start over. So we're back at node. Everything's a node. So we hit that, so we need to grab it. And then we can go to the left, get our 8, and now start going to the right again. That pink guy just keeps flying everywhere. There we go. I'll stay in this time. Going to the right, we already grabbed that, and we're all the way over here at the end. So it gave us a different order on the same data. The root's the first one. Then we walk down. As we walk down, then we come back a little ways, walk down, come back a little ways, and if there's more elements, we'd walk down, come back a little ways, walk down, come back a little ways, walk down. So it scatters our list around with a set pattern, right? Perhaps think of it like flipping through a textbook looking for pages. We don't flip every single page looking for a particular spot in the book, right? Oh, I do have a book. First, we grab a big section of pages. That's up to chapter 1, no further than that. Grab a big section of pages. Chapter 3, further than that. Grab a big section of pages. Chapter 4, okay, might be getting close now. Then we start going by 1 or 2 pages at a time until we get to the number we look at. So that's what our prefix is giving us. We grab a section and then flip through that section. Then we grab a section and flip through that section going downward. So depending on the data that we're looking at and what we want to look for, the natural order to it might make more sense. Or to do it in sections, kind of like when you grab a book and need to look up something you know is in chapter 7. Right? You start flipping groups of pages, and when you get closer and closer and closer, those groups of pages get smaller and smaller until you're flipping 1 page at a time. And then eventually you're looking at a paragraph at a time. So small sections and goes downward. Then our last one on postfix is the one that actually kind of used the most, but some of that used the most might be the thing I was talking about earlier. That's how calculating. This is how we actually pass in operations. So a postfix binary tree is up there with like a stack. It's one of the ones that's almost natural for a machine to do. So kind of an important thing. So left, then right, and we grab the node last. So we're going to start up here at the root, but we don't want the root. We want to go left as far as we can. So we're going to grab 3 first. Now we need to go right. So we'll come up. That's a node. We don't want the node. Try to go to the right. And once again, we can go to the left. We need to go left as far as we can. And then we get our second one, 8. And now we can go continue rightward again. Come back up. Oh, there's nothing to the right. So now we can grab this node that we just left off of. Then we can grab our 14. Then come back and grab this node that we already did the left and right for this node. So left, then right, then we come back and get the node in between it. So then we got a 7. And that finishes our entire left branch. So now we need to go to the right. So, well, our root is the node, and node is, it's postfix, so node is last. So go over to the right, grab that 52. And that's as far as we can go to the right. So now we can come back and grab our node of 19. That wasn't enough numbers to see the pattern. It's the opposite of this one. So we have small sections that walk down. So we walk down, then we go back up and walk down, go back up and walk down, go back up and walk down. There's not enough to see the pattern here, but we walk up on a small section, then we go back down and walk up, then we go back down and walk up, go back down and walk up. So it gives us different ways to search through our data, depending on how it's organized. We have alternate ways to iterate through it instead of just straight through. And that can give us a lot of different improvements in the case of like how a calculator works and how a human needs to press the buttons on a calculator, right? Number, operation, other number, as opposed to a computer needs operation, number. It allows that translation But it gives us different ways to search through our data and different ways to organize. In order isn't always the best thing. Yeah, it shows up a lot in high level mathematics, depending on what we're doing. 1, 2, 3, 4, 5, the order numbers go in, isn't always the best order. Depending on what math we're doing, especially in high level mathematics, get into various sorts of groups, it might kind of fall apart, or in dynamical systems, chaos sort of things. Things with bifurcations, the traditional number for orders is not is a really, really bad one, because 3, if we just keep doubling stuff, 3 is the least likely number to ever occur, which means it should be near the end of the order of numbers, not the beginning. But it gives us a different order, so depending on our data set, one of those might be better than the others. And we saw the code for making this isn't much. It's a lot like the linked list, only we need that extra little step in there. I wrote it on the board, I'll go ahead and write it on here as well. Might as well, because that kind of filled up our time. This will be an important one though, because it's easy for a programmer to implement, and we get pretty good efficiency out of it. The stuff we're going to talk about Thursday is a lot harder for a programmer to implement. Excuse me. We will get much, much better efficiency out of it. It will move a whole lot quicker, but it will take some work on our part to make it work. Binary search trees are a lot easier. I'll just add it to this list. New Java class. I'll just call it a BST, and yeah, I'm not going to implement it. I'm just going to do the basic one. I'll just do a tree node, because that's all we need to look at, and then the tree connects all those nodes together, kind of like the list did earlier. This is the part we need to look at, and I started to call it BST, which, by the way, if you you can search for that, BST Java, and notice Google automatically search for binary search tree. I was going to make another comment there, but I'll skip the other comment. And you can see a reference, but just like the list we were looking at earlier, a lot of your reference material is going to use recursion, because that's a common computer science classroom problem to practice recursion in. So you might want to take a moment and redo it as loops, because then it's a lot easier to make sense of. But our node itself is, like we saw, well, we'll need a generic type, but it can't just be any generic type, because we have that specific restriction, smaller to the left, bigger to the right. So we need a generic type that implements comparables. Is that not the right? What's the word I need there? Java generics. Nope, not in that. Nope, not gonna help, not gonna help, not gonna help. This T, nope, that doesn't help. T and G. There it is. Oh, extends. Can't implement it, extends here. So comparable is an interface, but we use the keyword that we would normally use for inheritance. And remember, an interface is like a plug, right? Like these KVM switches here in the lab. There's HDMI, 2 USBs. I assume one of them is USB 3 and one of them is USB 2. And and then TRS, some 1/4-inch TRS ones. Probably one's input, one's output. One's for mic, one's for headphones. But we have different specific sizes of plugs, so we know anybody comes in here with a laptop, and those KVM switches will interface with the laptop, and then they can use they can extend their laptop into the desk of the second computer. They can use the monitors on the desk instead of the laptop monitors, or it connects things. But an interface is the same thing, just virtually. But when we do it with generics, we need to extend instead of implement. We actually need it to be that type. So that means whatever our generic type is has to have the compare to method. So we have left and right. Otherwise, our node is a lot like the one we had earlier. We have key data, we'll call it element. Oh, might as well follow good form and make it private. Private generic data type element, the thing we actually want to store there. And then we need another tree node. Actually, we need 2 of them. One of them is going to be left. Private tree node right. And then we can just loop through like we did earlier, iterative stuff. So while the element we're looking at, right, in the list, we just kept going next till we got to the end. There's not another get next is null. So we need the comparison too, right? We start at 19, set that up as our root, and then we have a method that iterates through. So add 7. So our method, well, we start at the root. If the new element is less than the current element, we go to the left. Go to the left. Or it's null. Well, it's null, so we'll pop that element in there. Then same thing, and then we keep doing that. A 3. Start at the root. If the new element is smaller, we go to the left. Go to the left and repeat. It's not null. 3 is smaller than 7, so we go to the left. Go up to 52. Start at the root. If not null, so root's not null. If less than, then go to the left. Well, 52 is not less than, so we're over in our else structure. Bigger than, so we go to the right. Oh, it is null, so we pop our 52 in. Go left and right based off that comparison. And when we hit a null spot, kind of like we did at the end of the list, that's where our new element goes. And just keep looping through until we add everything. And then set up some ways to traverse it. There's an example right in your book, but notice how little is actually involved in making that. So there's not much to it. You'll want to give it a try. To start with, mostly at this level, be aware that it exists. As you progress further, remember you have a lot of advantages to it. If you need to translate between human order and machine order, kind of like a punch button calculator, traditional TI calculators, humans punch it in the order humans deal with math, but it has to be translated to the order machines deal with math. That translation will need a binary search tree. Otherwise, we have some advantages. It speeds things up. And usually when we're in situations that what we call depth first searches where the only possible option is to check every single option. A binary search tree is a quick way to implement that, because no matter what we're doing, we have to look at every single. So if we have to look at everything, there's no way to improve. But here we have 3 different options of how we iterate through our list. And think of it that way, some progression there. Let me start with there's definitely a binary search tree in the textbook. So you can look at the example there. It'll use recursion, so do like we did earlier. When I gave up on trying to do recursion earlier, because textbook has. Yeah. Let's just go with the easy one. We just need to implement it. This isn't a computer science class, this is software development. We're not studying the finer details and putting together controlled experiments. We're creating software, we're developing software. There's a difference between software development and computer science. So translate those recursion things to loops to make it easier to figure out what's going on. Really be aware of binary search trees and when you would need them. If you need options on how to iterate, a linked list only has one way to iterate through it. But this gives us 3 ways to iterate through a list of data. And we get drastically different results. In order, or think of that analogy I pointed out like a textbook. We don't start at page 1 and go page by page to look for something in Windows in chapter 7, right? We start grabbing groups of pages. Chapter 2, not quite there, grab a group of pages. Chapter 3, not quite there, so we grab a group of pages, and then keep grabbing groups of pages, and eventually we get up to chapter 7. And then we can start going page by page to find it. So it groups our data to accelerate the search. Random spot, walk down, go back up, go down, go back up, down like a wave. And then this one goes the opposite way. Down, we go down, and then we go up. Then we go back down to another starting point and go up. Go to a down starting point and go up. So mostly just be aware that it's there and how it improves the way you can search through a list. Iterate through a list. You don't need to go through the whole list at once. Because then we can add little simple selection structures in. Right? We can start complicating it and add selection structures to jump way ahead in the list. If we see where our grouping is going to be, we can start to get an idea of it and add selection structures so that we jump 5 groups ahead. Because that way, there's a whole lot of stuff we don't have to lose. But that's starting to complicate the matter. For now, be aware of the basic premise of what it does. It gives us alternative ways to iterate through the list. And we'll make that translation between human order and machine order. Because that's an important one as well, because we do this stuff for humans, right? We're not doing it solely for the machines. We're making software that humans are going to use. So that translation will be important somewhere as well. Play around with the list thing. That's my suggestion. We have 25 minutes left in class time. We use that productively. I would suggest that I already put that list one up on GitHub. I'll put actually there was nothing there. That was that quick look at the binary search tree node. You all can recreate that. We need element left and right. Not much to it. But the other one's up, the list from earlier is up on GitHub. So if you want to download that, play around with that, add some stuff, that's my recommendation. Otherwise, does anybody have any questions? I see head nods here in classroom. Okay, I assume 5 seconds silence means no questions. So that'll be it for this evening. And on Thursday, we will look at more data structures like graphs and spanning trees and heaps. I want to get through at least those 3. And then depending on what the clock on the wall says, I have a list of about 50 other things I can start choosing from until we run out of time. So I have 3 that I know we're going to get through, and then fill the rest of our time, because that way you'll at least hear the words before somewhere anyway. And then when you need the stuff later, you'll have heard the word and kind of have to. Otherwise, you all have a great evening. If you have any questions, let me know. I will see you all on Thursday.